Welcome students. Today we are going to discuss about autonomous equations and their application to population dynamics. So first of all, what are autonomous differential equations? So first order differential equation, it's called autonomous if the right hand side of f does not depends on t. For example, if I have dy by dt equals to y, or dy by dt equals to some function of y. So such a differential equation is called autonomous differential equation. Now clearly autonomous differential equations are separable. Why are they separable? Because if you look dy by dt equals to f of y, you can bring dy over fy one side and you get what? You get dt on the other side. So you have managed to separate y and t. So that's why autonomous differential equations are separable and hence they can be solved. For now, we are mainly interested in the qualitative behavior. All right. So we'll try to see the qualitative behavior. Note that qualitative behavior is trying to understand how does the solution behave without actually finding out what the solutions are. And we can get some important information in these differential equations without solving them. So we'll discuss the equilibrium. So of autonomous differential equation is y prime equals to ry, where y0 equals to y naught for some y naught. So this is an initial value problem. The most basic one can be applied to the population growth. So this represents, if you recall from your math 151 or 152, this represents an exponential growth. So this simple model predicts the population changes at the rate proportional to the amount of or the size of population. So y prime equals to ry and y0 equals to y naught, where y naught is some starting point for the population. Now this is a separable differential equation, and we have already seen that the solution to this is going to be yt equals to y0 e to the power rt. Now note, based on R, you can see what will happen to the population. So if R is greater than 0, then we'll have exponential growth. What does it mean by exponential growth? It will follow an increasing exponential function. 2, if R is less than 0, we will have an exponential decrease in the population, or we'll call it, we'll have an exponential decay. So recall this was used also in radioactivity, this differential equation. Now, this is the most basic model. Now, this model is unrealistic, right? Unrealistic. Why is it unrealistic? Because if you take limit as t goes to infinity of the solution, you will get infinity if r is greater than 0, right? So this doesn't happen really, right? The population will not go to infinity. So it is okay for limited amount of time. Means the population growth will follow the exponential growth for a limited amount of time, but cannot be the case, can't be the case long term. Yeah. Similarly, about the number of patients of COVID, the discussion was that the growth was an exponential growth, but now you see that it has basically flattened out. So we'll discuss a modification to the exponential growth, and that modification is called logistic growth. So in logistic growth, you have basically, again, it's same, y prime equals to ry, but multiplied by extra 1 minus y by k. And again, y0 equals to y0, that is the initial value. Here, r and k are the constants. R is called the intrinsic rate of growth. Now note that if k is infinity, if k goes to infinity, what happens? In this case, y over k will go to 0. In that case, the model will simplify to r times y. So it will simplify to the exponential growth. Now let's try to understand some qualitative observations. Again, we won't solve it. We will try to understand qualitatively how the solutions look like. So first observation, so observation 1, if y is very small, for y small, this will be almost like 0, right? So in that case, if y is small, your y prime is roughly equals to ry. And we expect, and then we expect what growth? Then we expect exponential growth. So for small y, we expect the exponential growth. Secondly, what happens if y is roughly k? If y is roughly k, then this part is going to be roughly 1. That means 1 minus roughly 1 is going to be 0, right? So if y is roughly k, then we have y prime is roughly going to be 0. This means there is a very little growth once the population gets close to what? K. Once population is close to K, right? So if you draw this, this is how. So if you look at, this is the population. So these are the estimated populations. So U1 high is given by the exponential growth. Exponential. And these are different models. Okay, so these models are different models. So now we are trying to understand the qualitative behavior. So for exponential function, we understood it right away, right? Do you agree? That if r is greater than 0, then we'll have exponential growth. If r is less than 0, then we'll have exponential decay. So there's nothing happening which is of a deeper meaning or reason. But let's try to understand the logistic growth now. Let's do a qualitative analysis of autonomous DE. So consider a solution. So consider an equilibrium solution. So consider a solution phi of t equals to y such that when you take y prime, you get 0. So such solutions are called equilibrium solutions, right? So either this happens or you get f of y is 0, right? So these are called equilibrium solution. The idea behind the word equilibrium is that you are kind of stabilized at equilibrium solution, right? Because the derivative is 0 You are neither seeing an increase nor you're seeing a decrease. So let's understand the equilibrium solution of logistic differential equation. So we have y prime equals to r times 1 minus y over k times y. So we get y prime equals to 0 implies the right hand side is 0. Now this is 0 would imply either y is 0 or 1 y minus 1 equals to y by k, that is y equals to k. So these are your equilibrium solutions. So now we have found out the equilibrium solution. We'll try to understand the direction field of this autonomous differential equations. However, before that, we'll try to understand what is called as phase lines. So what are these phase lines? So phase lines of an autonomous differential equation, y prime equals to f of y, is constructed by plotting f of y against y and then using the left or right facing arrows to denote the region where f of y is negative or positive. So what does it mean? Let's draw one for this one. So for logistic growth, we have y prime equals to r 1 minus y over k times y. So this is your f of y. Yeah. So your f of y is so it's a quadratic equation in y. So it is a parabola. Now you want to draw this parabola. So how would you draw it? Well, one way is to find the vertex of the parabola and then draw it. The other way is to basically look at the maximum point of this and then draw it. So because the sine of y square is negative, it will be upside down parabola. So let's see what is the maximum value for this parabola. So we have f prime y is going to be, so let's multiply this out here. We get minus y square times r by k plus ry. Right. So now f prime y is going to be minus 2 y r over k because r and k are constant plus r. So f prime y equals to 0 implies minus 2y r plus k, sorry, divided by k plus r equals to 0. This would imply y equals to k divided by 2. And what is the value at, so f of k by 2 is going to be, when you substitute k by 2 in this equation here, you will see that that is going to be r k by 4. So this is how the inverted parabola looks like. Here you will have this height corresponds to k by 2. Here you will have k, because these are the zeros, right? What are the zeros? Zeros are y equals to 0 if this part becomes 0, or y equals to k. So these are the zeros of the parabola. So I draw it like that. and this is the maximum height here, and at this value we get, this value is going to be rk by 4. So now let's determine the signs basically for our y prime. So now what you do is you draw, so first you draw y, f of y against y. So that we have done already. Then you draw the left arrow or the right arrow to denote the region where f of y is negative and positive respectively. So you will use the left arrow where f of y is negative. So the left side pointing arrow here would be in this, here f of y is what? F of y is negative, right? F of y is less than 0. So I will draw an arrow in this direction. What about here? Here f of y is positive, so I'll draw an arrow like that. I'll draw an arrow like that. Similarly, in this case, I'll draw an arrow in the opposite direction, although for population growth, this does not apply, right? Because, well, f of y is never going to be negative for the population growth. Does not apply for population growth. So we'll see how the phase lines help us draw the direction field. So now the phase lines can assist us in drawing what? The integral curves of the direction field. So notice the following, first of all. So this is the direction field of the previous equation. We'll see how to get to this from the previous one. So notice that here, what? Here, this is your equilibrium point. The other equilibrium point is this guy. Now here, so first of all, K is what is called as stable equilibrium, right? Because the solutions are converging to it. So you called an equilibrium point as a stable equilibrium point if the solutions are converging to it, right? And how can you see that from the direction, from the phase lines? You can see that from here because both the signs are pointing towards K, arrow signs. So this is what gives us a stable equilibrium. Yeah. So you'll get a stable equilibrium at any point K if you have solutions pointing in both directions. You will get an unstable equilibrium if you get, either like that or you get like that, right? So these are not stable equilibrium because the solutions are going away from it. So this is not stable equilibrium here. This could be called as semi-stable equilibrium, right? Because at least the solutions are converging in one direction. Let's see how the phase diagram is going to help us to understand all these. Okay, so let's move ahead. So here you can see the integral curves are what? They are concave up. And they are what kind of function? They are decreasing function. And again, we want to be able to see this from the phase diagram without having to draw the integral curves. So first we'll investigate what is happening in the integral curve. We'll go back to the phase diagram, investigate, and build the connection. So this is what we are trying to do. Here at k equals, y equals to k, you get an asymptotically stable equilibrium. Why is it asymptotically stable? Asymptotically because as t goes to infinity, your solutions converge to this equilibrium point, right? As t goes to infinity. So whenever you are looking at the behavior as t goes to something infinity, then you talk about the asymptotic. Now in this part until here, If you notice until here, the integral curves are concave down and increasing functions. In this part here, you can see that the function is still increasing, concave down. Sorry, in this case, it's concave up though, right? You can see that the integral curves are concave up. You can see from this red part here, right? Or you trace any of the integral curves, you'll see that it's concave up. Increasing function. And this is our unstable equilibrium because the solution is going away from it. So note that these solutions will never touch line y equals to 0, y equals to k, because these are guaranteed by the theorems in from 2.3, all right? That why? Because these are equilibrium solutions and the solutions do not intersect, right? So that is what we are guaranteed, okay? All right, so now, again, the question is, how can we read all this from the phase diagram? Oh, sorry, phase line. How can I read all of this information from the phase line? What information? The information about the shape of the integral curves. You've already seen how tedious it is to draw direction fields without, without much information, right? So let's see how we will proceed with this. So we are interested in the curve plotting now. Now to determine the shape of the integral curves, you need to calculate the second derivative, right? Because second derivative decides how the shape is going to be, whether it's going to be concave up or concave down. So how do you compute that? So note that what is your d by dt of f of y? This is going to be df by dy times dy by dt, right? So what do we get? We get d square y by dt square, taking derivative on both sides with respect to. So you have y prime equals to f of y, right? If you take derivative on both sides, you get one side, you get d square y by dt square. On the other side, you'll get derivative of this, which is f prime y times dy by dt, which is again, but dy by dt is same as f of y. So you'll get f prime y times f of y. Now note that you can just look at the, so if d square y by dt square is greater than 0, then the function is concave up. And if it is less than 0, then it's concave down, right? So we'll do that for our logistic equation and determine where it's concave up and concave down. So let's see, y prime equals to r 1 minus y by k y, right? This was our logistic equation. So we need to compute this for our logistic equation. So f of y in this case is f of y is r times 1 minus y by k times y. We have already computed f prime y, we have computed early on here. So f prime y was minus 2y by r divided by k plus r. So we have f prime y is going to be r minus 2ry by k. So therefore, I can write d square y by dt square following f prime y times f of y is going to be r times, let me write f of y first. So 1 minus y by k times y multiplied by f prime, I can pull out r common from this guy, right? I can pull out r common. So I get r times 1 minus 2y by k. Now, first we need to determine the intervals of concave up and concave down, we need to see where does this second derivative become 0 or does not exist. It's a polynomial, so it will always exist. So d square y by dt square equals to 0 implies either, again, we get y by k equals to 0. So we get y equals to k. Or we get from here, you will see from this part, you will get y equals to k over 2. Or from the third part, you get y equals to 0. So these are the possible inflection points. So now let's try to look at the sign diagram of this and see where it is positive, where it's concave up, and where it's concave down. So what are the points? So we have 0, we have k by 2, we have k, we have further after k. Now let's see. So what is the sign here? So notice this guy. So here in this range, you can see that f prime y is going to be greater than 0, and f of y, what do we have for f of y? We have already computed that, so we should patch that information. So f of y is basically greater than 0 from 0 to k. So here f of y is greater than 0. So let me write that information down. So f of y is greater than 0 here, f of y is greater than 0 here, and f of y is less than 0 here. Now what about f prime? F prime is this linear function. So it will change the sign after k by 2. So here it becomes is greater than 0 here, less than 0 here. Then you will have prime y. And then here f prime y is going to be less than 0. So now what is the net sign then? Net sign. Net sign for what? Sign for y double prime. So here negative times negative makes it positive. Here it will be negative times positive, negative. And here it will be negative times negative, so positive. So your integral curves are going to be concave up here, concave down here, concave up. Yeah, so concave up, concave down, concave up. Yeah, so now let's refer back to the direction field, right? So what did we have? We had the following, that in 0 to k by 2, we had concave up, and what the direction fields were positive, right? So that means the curves were increasing. So 0 to k by 2, 0 to k by 2, the curves are increasing and they are concave up. Now from k by 2 to k, what is happening? From k by 2 to k by 2 to k, the function is concave down and the derivatives are negative. So the integral curves are basically what is happening to the integral curve. They are, so dy by dt is the integral curve measurement. So dy by dt is positive. So it's again increasing. Yeah, so this is measuring the how the curves are increasing or decreasing, because you have y prime equals to f of y, right? So in this case also, you see that it's increasing, but in concave what way? Down way. And similarly beyond k, f prime y is less than 0, so it is decreasing, yeah. And in what way? In concave up way. So it is decreasing in concave up way, yeah. And then you have the stable equilibrium point, which is k, and unstable equilibria, which is 0. So you see, if you had the phase lines, you could actually make sense of the whole integral curves, at least the nature of it, without having to find out, compute the direction field at every point. Now let's try to have a quantitative analysis of logistic equation, even though we said we won't do it, but let's try to get to the quantitative and then we can compare a bit. So we get dy by dt is going to be f of y, which was r1 minus y by k times y. This is a separable differential equation. So this is separable differential equation. So if it's a separable differential equation, you separate it to integrate, right? So you get dy by 1 minus y by k times y equals to r dt, and then you want to integrate on both sides. So this part, the left-hand side, has to be done by partial fractions, right? That's the only way out here, or at least that's the only easy way out here. So I will try to apply the partial fraction. So we get 1 upon y over k times y equals to a upon 1 minus y over k plus b upon y. And then when you cross multiply, this would give me ay plus b times 1 minus y by k equals to 1, right? Now from here, we want to solve for a and b. So notice that when a is 0, you get b equals to what? So when a is 0, we get what? We get b equals to, when a is 0, you get b equals to 1. And when b is, so when y equals to k, so let me write down how do I get to a and b's. So when y equals to 0, we get b equals to 1. And when y equals to k, this gives me ay equals to 1, or gives me sorry, my bad, when ak equals to 1, so I get a equals to 1 over k. Okay. So now we can put back our equation. So this integral I, so therefore, if I write I, it's going to be integral of 1 by y plus 1 by k divided by 1 by y by k dy equals to integration of rt, which is going to be rt, integration of r dt is going to be rt, plus some constants. Now this is going to be ln of y, ln of absolute value of y, plus, so if you take integral of this is going to be ln of 1 upon y by k equals to rt plus c. You can multiply it out here. So ln of a minus ln of b is going to be ln of a by b. So we get ln of y upon 1 minus y by k is going to be RT plus C. Now note that this is positive. Why is it positive? Because we are discussing the population growth. So Y is greater than 0. And also Y is less than equal to K. This would mean what? This would mean Y is by K is less than equal to 1. In fact, we'll take strictly less than because that is the maximum it can achieve. So Y by K less than 1, or we get 1 minus Y by K is greater than 0. So both of these numbers are greater than 0. So I can forget about the absolute value sign. So I can write it as now e to the power RT plus C equals to Y upon 1 minus Y by K. And then a little bit of rearrangement can basically give me that Y divided by, so Y times K upon minus KY equals to e to the power RT times e to the power C. Let's call it another constant, say another constant. Let's call it as a capital C. Okay, so this is going to be e to the power RT times C. Now we need to apply the initial condition. So the initial condition is basically, what is the initial condition? We are given Y of what? So let's go back and see. Y of 0 is Y0. So in that case, we'll get, when you substitute Y of 0 is Y0. So Y0 minus K by Y0 equals to, this is going to be, this part is going to be 1. So this is going to be C. So therefore, what do we get? We get Y of 0. Sorry, this is going to be Y of K, right? So therefore, we get the following. We get YK upon K minus Y equals to e to the power RT multiplied by Y0K divided by K minus Y0. So little bit of rearrangement will give you, you can see that YT is going to be Y0K Y0 plus K minus Y0 e to the power minus RT. Yeah, you can check that out, where your Y0 is between 0 and K, right? Okay. So now let's try to see, is it a valid solution? So let's see, limit as t goes to infinity of this is y of t is going to be, if you take t goes to infinity of this, it's same as taking t goes to infinity of this part. So this will become 0 as t goes to infinity. So you'll have y0 by k, y0k divided by y0. So you'll have y0k divided by y0, which is k. Yeah. So there, that means k is a asymptotically stable equilibrium. And y0 is unstable, right? So this is the whole analysis of logistic growth. Okay. All right. So that's the idea behind it. Now we can have, so we started, note that we started with the exponential growth. We went to logistic growth. All right. Then we have another model for population. It's called critical threshold. So what is the critical threshold? So in certain situations, the population will die out if the number of individuals decrease below a certain threshold value. So to model that IBP, we'll have the following. We'll have y prime equals to minus r times 1 minus y by t times y, with y of 0 equals to y naught. Now, if you compare this with the logistic growth, you will see that it was almost like a logistic growth, but there's a minus sign here. And instead of k, you have t, which is the threshold value. Now let's try to draw it. So recall when you had a plus sign here, instead of this guy, when you had a plus sign, it was an upside down parabola. So now because we have minus sign, we'll have downside up parabola. So you can see if I draw the phase lines, so in this case, because f of y is negative here, so f of y is negative, you will see that this is what will happen. And here also f of y is positive here, so you will have this thing happening. So this point T is an example of an unstable equilibrium. Okay. So now if you want to look at the phase line, integral curves, you will notice the following. So this is your equilibrium. Even though it's unstable, it's an equilibrium. If you notice the following here, so if your y0 is greater than t, then your starting point of the curve, the first values will be here. And in that case, you will see that y increases exponentially or without bounds. Now, again, that is not really a proper model. I mean, like, it should not exponentially, nothing should exponentially blow up, right? Because say, suppose even on Earth, I mean, like, there's a maximum carrying capacity of the Earth. Yeah, actually, that is modeled by the letter K in the logistic growth. That thing K is called carrying capacity. Anyway, so let's come back here. However, so this is the threshold value. If you're below this, so if your y0, if your starting point y0 was between greater than t, then you see the solution dies, or decays to what? To 0. That means what? That there is a decay happening. So above that threshold t, the solution basically blows up, goes exponentially, and below that it basically goes to 0. So this is another model, but this is not again a good model, right? Because if you want to look at the solution of this quantitatively, so the solution of this is very similar to the solution, right? This equation and this equation are very similar. The logistic growth solution equation. The only difference is that there's a minus sign in front and there's a K. So I can just copy over the solution I got in the logistic growth with a little bit of care. So you will see y of t is going to be y0t over y0 plus t minus y0 e to the power rt. Yeah, so please check yourself. Now, the idea is, well, if limit as t goes to infinity, t goes to infinity of y0t upon y0 plus t minus y0 e to the power rt. This is 0 if what? If y0 is less than t, greater than 0. Yeah. So now, so you can see that, however, if if y0 is greater than t, then the solution is slightly tricky. So y0 is greater than t. We'll see that y0 plus, let's see, when does this denominator becomes closer to 0? In that case, because if denominator becomes closer to 0, the numerator is fixed value, and the denominator becomes closer to 0, that means it will basically, the solution will what? Blow up, right? It will become very large. So let's see, this is 0, implies when I solve this, I get t equals to, so you multiply on the other side, solve for t, you will get t equals to 1 upon r ln of y0 times y0 minus t. So what is the problem with this? The problem is that the solution, so now your y0 is greater than, so y0 is what? You have y0 greater than t, so this is positive, this is positive. So this makes sense, all right? I'm not writing an expression which is not undefined. So now if y0 is greater than t, you will see that solution becomes unbounded quite quickly. So this is a finite number, so it becomes unbounded in finite time. So note that you were unable to see, this was not clear from the DE. Yeah, we needed to see the solution, for this. Right? But however, you could have made that prediction that it's blowing up here, right? It's going to infinity. Okay. So again, such a model is not a good model, right? I mean, like if your y0 is greater than t, it's like saying that if you start with amount of the population, initial value of the population is beyond this critical threshold, then the population blows up. Again, that is not the realistic model. So what we'll do is we'll combine the logistic growth with the threshold model and get next model, which is a logistic growth with threshold model. Of course, the name indicates it. Now, this is given by the following initial value problem. So again, the differential equation for that is y prime equals to minus r times 1 minus y by t. So this part was for times y. This part is for your critical growth, threshold growth. And then you put this for logistic. And this is a differential initial value problem, which basically has both of it in together. Let's see, what do we get out of this? So again, you need to basically look at the sign of this to draw the phase lines, because phase lines will tell you everything. So here, let's see. So we have, what are the points? So where does y prime become 0? So y prime becomes 0 at what? At 0. It becomes 0 at t, and of course it becomes 0 at k. Yeah? We are assuming here that the carrying capacity, we are assuming that k is bigger than t greater than 0. Yeah, you get the significance out of when you're trying to actually model a population. So k is the maximum capacity of the population. T is the critical threshold model. So sorry, T is the critical point beyond which the population will still survive. Below this, the population will decay to 0. All right, so here we have that. And of course, R was also greater than 0. So I should have mentioned that when I was giving you the initial value problem. So when you look at the phase lines, you will see that here, this is how the y versus f of y looks like. So in this case, you will see that here f of y is negative, so you get negative. The direction is left. Here the f of y is positive, so it's this way. In this case also f of y is positive, so this way. And here it's negative, so other direction. And here we get what? So now let's analyze this. So what do we get? We get in this case y equals to 0 is a stable equilibrium. Note that this part does not really exist when you're discussing the population, but that's fine. Or does it? Well, let's see. What does it represent? It represents y. Y is the population, right? So it does not exist. Okay. Now here, if you look at y, because they both are going away from it, sorry, if you look at t, the both solutions are going away from it. So y equals to t is an unstable solution. Stable solution or unstable equilibrium. What about this point? Now, at this point, both the solutions are converging to it, right? So this is a stable equilibrium. This should be reflected in your graph as well. Oh, sorry, in the direction field as well. So k y equals to k. You see the solutions are converging to it, right? So again, in what way? Concave up or concave down? That you have to do the similar analysis as you did earlier. This is your t solution, y equals to t. Is it stable or unstable? It's unstable because both the solutions, see, down the solutions are converging away, up also the solutions are converging away from it. And y equals to 0, the stable solution, because the solutions are converging to 0. So this is the model of logistic growth with a threshold. So that's about it for today. Thank you for your attention.